let's recall what a zero is. What's a zero? Zero, very closely related to solutions and roots, right? It's the value that if you have a polynomial, like say this, right? This polynomial can't be, you can't solve this because it's not equal to anything. It's not equal to a number, okay? But I can still put numbers into it. For instance, -2, which is going to be 4 minus 10 plus 6. That make the entire polynomial 0, okay? And that's why they're called zeros. So if you have a polynomial of degree n, how many zeros will it have? Now, n is right, sort of, okay? Kind of depends how you count, right? I'm going to keep this as our answer, but you need to put a condition on it, right? Namely, which of those zeros are real numbers, okay? Now the answer is, none of them may be real, some of them may be real, or all of them may be real. Okay, so what does that mean? Let's just do some simple examples, okay? We'll keep the degree nice and low so we don't get too confused. But take, for instance, x squared plus 5. Okay, now if I want this thing to be equal to 0, find the values that make it 0. Okay, x squared plus 5 is equal to 0. Then I'm going to get a negative value on the right-hand side and a square on the left-hand side, right? So what I've got here, plus or minus the square root of 5i, okay? In this case, there are 2 zeros, but neither of them are real, okay? Alternatively, obviously, in normal cases, you know, both might be real. In order to get some, okay, let's raise the power a little bit. So if we did say, you know, p of x is equal to, or I don't know, x cubed, probably should have thought of an example beforehand, plus x. No, that's not going to do it. I think I need a number on here. Actually, I'm just gonna leave it. When you have a cubic, I'm going to draw it for you. Okay? Because you've got 3 zeros, right? 3 zeros. You may have all of them being real. Okay? So 1, 2, 3. No problems. Okay? But if I move it up, okay, just shift it upwards, like so. Okay? I now only have one of them being real, while the other two are, well, they're going to be complex. I suppose we could make one up. Let's just do it, I guess. If I do p of x being equal to x times x squared minus 1. So if I just do this. Okay, so there's the first graph that I did, right? 3 zeros, they're all real, minus 1 0 and 1, okay? But if I move this graph up far enough, okay, for instance, if I move it up 100 units, okay, I don't know what it will be, but when I solve this, I'm going to get this scenario. I have one root, it'll be a different one from before, okay? And then because these are so high up, only one out of the 3 will be real, the other 2 will be complex, okay? So, this is the first property, okay? But it's sort of said in more common ways, namely, let me get rid of these graphs, right? This is why I said it's 3.5. Call this one A, maybe. Come in. Hi. Thank you. Okay. If a polynomial of degree n has n zeros, right, and some or all may be, some or all may be real, okay, we usually actually are just interested in the real ones, okay? So the way this more commonly gets said, and it's in the program like this, is that a polynomial of degree n cannot have more than n zeros, okay? So what this is opening up the possibility is you might have 0, 1, or 2. Sorry, yeah? Thanks. Okay, so you might have some or none or as many as you have of the degree, okay? To ground that in graphing, which is how I kind of proved it, right? Here's yet another way of saying it. which is that a polynomial equation, okay, so if it's actually equal to something of degree n, it can't have, now you've got to be careful because sometimes sometimes even the textbooks get this wrong. But if it's an equation, it doesn't have zeros. It has solutions. Or if you're graphing it, it has roots. Okay? So these two really, I hope you can see they're the same statement, just in different contexts. If you want to make it even clearer, you could add the word expression in here to distinguish it between an equation. Expressions don't have to have equal signs in them.